Welcome back, Focus Learners. We are jumping right in today because we have a genuinely fascinating mission ahead of us. We're going to decode the rather complex process of installing a new psychological part in a low-verbal learner. But, we're totally ditching the traditional clinical jargon today. Instead, we're leaning into a brilliant software engineering metaphor drawn straight from foundational NLP, neurolinguistic programming. We're actually going to use the hypnotic create a new part pattern to write brand new code, looking at human communication completely through the eyes of a software architect.
Okay, let's dive into this. If we truly want to change how we interact, we absolutely have to change our core assumptions first. We need to stop looking at a low-verbal individual as someone who, quote-unquote, can't communicate. Instead, look at this quote right here. They are a system that is intentionally conserving resources. They're just in idle mode. Their input/output ports simply have a massive barrier to entry, literally, to protect the system from crashing.
And to navigate this, we've structured today's explainer as your official system documentation. So we'll start with the low-verbal operating system, move on to coding and autonomous initiator, go through the reframing protocol, debug our latencies, and finally look at preventing system thermal shutdown. It's a perfectly logical, structured blueprint.
Section 1. The low-verbal operating system. Now, what's really interesting about the slide is how we can seamlessly translate human quirks into actual system architecture. Silence? Well, they aren't ignoring you, that's just background processing. Gaze shifts aren't distractions, they're disk read operations. A single spoken word isn't a lack of vocabulary, right? It's a compressed file. And a shrug? That is metadata telling you there's a buffer overload. When we change our debugging approach to match this system, our whole strategy shifts from feeling frustrated to becoming analytically curious.
Section 2. Coding and autonomous initiator.
To get the ball rolling with a low-verbal learner, we literally can't just sit around and wait for them to start. We need to spin up a background daemon. Think of it as a program running silently behind the scenes. This is a completely new, autonomous part in our own psyche that initiates spoken conversations without relying on their immediate feedback. In NLP, this concept of a well-formed outcome is essentially your compiled executable. It means our instructions have to be hyper-specific. Check out our refactored criteria here. We use positive states, meaning absolutely no not operators, so we print hello. We rely on local logs for sensory evidence, like literally feeling our own vocal cords vibrate, because the external server isn't giving us that satisfying 200 OK signal. We define strict conditional triggers for the context, and crucially, this script must be self-maintained. It's gotta run even if the listener throws us an error 404.
And this brilliantly illustrates the exact network protocol we need to adopt. Normally, our everyday conversations are TCP connections. They require that synchronous three-way handshake to work. But with a low-verbal system, waiting for an asynchronous connection completely fails. We've got to switch our strategy over to sending UDP broadcasts. A UDP broadcast just pushes a data packet without requiring an immediate acknowledgement. You literally just state, "The weather is shifting today. End of transmission." If the packet successfully left your system, your code executed perfectly.
Section 3. The 6-step reframing protocol.
So how do we actually install this? Well, this right here is the core hypnotic mechanism for creating a totally new psychological part. We're essentially using the 7-step NLP hypnotic process, and we have to treat the quiet part of the learner, and honestly, even the hesitant part of ourselves, as a legacy security protocol that's just designed to prevent social buffer overflows. Here's the exact reframing logic mapped out for action. First, we access the source code by identifying the quiet behavior. Then, we open a port by simply asking that quiet part if it's willing to communicate. Step 3, we identify the positive intent. Usually, this old firewall is running a protect user function just to save energy. Fourth, we identify new libraries, asking the creative part for alternatives that still protect the user. Then we do unit testing to evaluate acceptance, followed by an ecological check to ensure no internal parts object. And finally, to cap off that full 7-step hypnotic process, we do future pacing, mentally rehearsing this new firewall in tomorrow's conversations. We are literally writing new subroutines that satisfy the old firewall's core desire to protect.
When we actually deploy this, we use very specific starter scripts. Now, for a low-verbal individual, we aren't aiming for deep philosophy here. We're deploying what's called phatic communication. We use practical subroutines like the observer, just commenting on a shared object, or the requester, asking for low-stakes data, or the phatic ping, a super simple, low-pressure greeting. These are scripts designed purely to perform a social task. It's just a low-voltage ping to see if the system is reachable.
Section 4.
debugging latency and silences.
Let's move to and see how this builds our understanding of latency. We use this really cool dual-axis latency model. It's a high-resolution performance map that plots vocabulary, so our libraries, against energy cost, which is our RAM. If they have low libraries and it requires high RAM to process, boom, they hit a blue screen. High libraries but the RAM cost is too high, that's a bottleneck. Low and low gets you idle. Our ultimate goal here is to act as an external API. We want to provide the libraries for them so we can seamlessly move the user toward that high libs, low RAM stream state, completely without crashing their system.
Part of managing that RAM is understanding physical cues. Remember, a gaze shift is a disk read operation. They are actively accessing internal hard drives. If they're looking up, that's visual memory. Looking down, kinesthetic memory. If you push for eye contact right here while they're looking away, you will literally cause a thread hang. You absolutely must wait for the system to return to idle.
So, the crucial point is that when they do reply, those single words are compressed files. You can't decode them without the header info. We have to use the NLP metamodel, which is a set of targeted clarifying questions to provide a Boolean choice. This helps them decompress the data without burning up excess RAM. Instead of an open-ended question that totally drains their memory, just ask fine as an acceptable or excellent. This acts as an incredibly low-cost 1 or 0 prompt for their processor.
And this brings us to a profound frustration for low-verbal learners, that identity-level conflict of not being known. At the very center of this system is a vulnerable person who desperately wants to connect, but the input-output overhead of explaining themselves is simply way too expensive. We solve this by pacing their metadata. We act as their external API, verbalizing what we see. Saying something like, "I notice you looked up, you must be searching for the right picture," provides the documentation for their internal process, entirely without demanding a response.
Section 5. Preventing System Thermal Shutdown. This is arguably the most critical phase of our system deployment, managing the physical and cognitive toll this new programming takes. Sometimes, after a really high-intensity session of communicating, a learner might exhibit narcolepsy. They might instantly fall asleep. We have to view this as a thermal shutdown. It is a protective power down. Sudden sleep isn't a failure, guys. It's an ecological signal. It absolutely validates that their internal code was running at peak performance, completely exhausting their system, and the brain basically forced to shut down to prevent hardware damage.
To manage this, we deploy a highly specific interaction timeline, the cooldown protocol. We have the peak zone in minutes 1 to 5, where we maintain high engagement while they're quote-unquote calling the shots. But as soon as we see latency increase, entering that yellow zone around minutes 5 to 7, we have to switch entirely to low RAM yes-no Boolean inputs. Finally, in the red zone at minute 7 and beyond, we shift completely to passive mirroring. We must initiate this graceful log-off before a hard system crash occurs.
Ultimately, what we're doing is engineering a safety buffer to effectively increase their battery capacity. We pull this off through modular sprints, short, intense bursts of interaction, alternating with necessary system idle time. We externalize libraries by providing visual menus, moving tasks from heavy retrieval to low RAM recognition, and we deliver a known outcome, a final validation packet just acknowledging their massive effort. In short, we act as a governor on their engine, generously taking over the heavy computing load for them.
As we wrap up this explainer, I want to leave you with a thought to chew on. What if the silences you encounter aren't communication failures at all, but rather necessary system updates? I challenge you, the focused learner, to permanently reframe how you debug your interactions with low-verbal individuals. Because when you truly understand the system, you can finally write the right code. Thanks so much for joining me today, and keep learning.